Okay, so you just did some work with sequences, and now we're going to transition to series. And most of our work will be with series in the end, but as we'll see, series have a lot of connections with sequences as well. So hopefully you remember the big idea. Series is obtained by adding up the terms of a sequence. And we use this sigma notation that, of course, we're familiar with a little bit from Riemann sums, etc. And so we've got sigma, we've got the terms of the sequence, and then we've got this thing called an indexing or dummy variable that just keeps track of where we're at. And so which term are we starting with, which term are we ending with, right? So it's sometimes a little confusing. This top number is not necessarily how many terms you added up. It's the last term that you added up. And so it all depends on where you start to determine how many terms you added up. So in this case, we're going from the mth term up to the nth term. So from the m term to the n term, right? And however many it takes to get there. And so that's all there is to the notation. And so we'll be looking at lots of series, and we're going to be interested in what happens when we add up lots and lots of terms, such as infinitely many terms in the series. So here's just a couple little examples. The good news is we're not doing anything with complex numbers, and so when you see I, it's just a good old counting variable. It's not the square root of -1 like we would have seen in pre-calc. So I simply plug in 3, I plug in 4, I plug in 5, I keep going until I get to 6, and then I add them up. Sometimes it's good to be able to work backwards and sort of start with a series and try and think about what the sigma notation would be. And we're just remembering that the indexing variable, whatever it is, k or n or I, is just going to be going up by a count of 1 each time. And so we sort of have to look for the pattern. This one's doubling, so maybe a 2k type pattern. This one's adding 1. And so sometimes it takes a little guessing and checking, writing stuff down. If it doesn't work, try and adjust it. And so in this case, if we start at 1, then the bottom is 2 more than that, and the top is double that. And if you just keep going, you follow the correct pattern. If you're not sure if this is right, just start plugging in a few values of k and make sure you're getting this back. There's nothing that says you have to start at 1 if it's more convenient or makes more sense to start at 0, which is often going to be the case for us, actually. You can start the count at 0, and so now I just sort of have to adjust these things. And so now I have to add 3, and I have to add 1 up here to get it all to work out. And so there would technically be infinitely many ways to write this in sigma notation, all depending on what value of k I started at, right? 0 and 1 probably the most common. And so sort of the last thing is just a key piece of vocabulary, and that is a partial sum. And it's sort of what it sounds like. We're typically dealing with infinite series. A partial sum will be part of that infinity. So it's just the sum of the first n terms. And so S sub n, capital S sub n, stands for the sum of the first n terms of a series. And so in sigma notation, we're starting at 1 and going up to n. And then it turns out that that's going to be sort of interest as we look at what's happening to these series at infinity. And so we are sort of wondering what happens to the sequence of partial sums. And so, okay, what if we just add up the first term? What if we add up the first 2 terms? What if we add up the first 3 terms? What if we add up the first 4 terms? Hopefully we can notice a pattern and say, okay, I can see what's happening to this sequence, so that will help me see what is happening to the infinite series. And it all gets a little abstract. You've got terms, you've got series, you've got partial sums, you've got a sequence of partial sums. There are lots of things to sort of keep track of, but when we start doing a few examples, I think it'll start to make sense. And for today, this is the example you're going to look at, sort of a particularly fun series, 1 over k times k plus 1, starting our count out at 1. And so I'm going to have you work in your groups again on a few things, and after you've worked for a while, then you can watch the next video, which will talk you through some of these details. And so when you get into your groups, you're going to be working on these few items. First, just get a handle for what the series looks like. So list out the first 5 terms, and then just make a prediction. What do you think is going to happen if you continue this forever? And of course, the big question is it just getting bigger and bigger and bigger? Is it diverging, or is it approaching some number? And if it's approaching some number, what number is it approaching? And then actually start doing some calculations. What happens if you add up the first term, the first two terms, the first three terms, and so forth? As it says here, it's going to be helpful in the long run if you write your final answers as fractions. And if you need to use your calculator to help you do the calculations and simplify things, that is totally fine. Then try and write a formula for the nth partial sum. Use that formula to see what happens when you approach infinity. And then think about what the answer to 4 tells you about this original series that we started this whole mess with. And so, like I said, work on this in groups. Use your calculator as needed to see what you can come up with. And then watch the next video.